Hello everyone, welcome to this presentation entitled How to create a TON controller for LTspice. In this video we will see first an introduction, then we will show the schematic diagram of the TON controller. We will present how to implement this controller in LTspice, and finally we will show several LTspice simulations to verify the correct operation of the controller. This slide shows the operation of a DC-DC converter under TON control. We are using here the buck converter as an example. And here on the right we have the waveforms corresponding to the gate, the current through the inductor, and a clock signal which is used in this circuit here, which is a programmable one-shot circuit. So the idea is that using this programmable one-shot circuit, we are going to fix the TON time of the switch. So once the switch is on, the current through the inductor is going to increase, as shown here, until the end of the TON period. Then at this instant here, the switch is turned off and the current is decreasing linearly, as we know, until reaching a minimum value, which is the valley current of the inductor. We detect this point here by using this comparator. So when the current through the inductor is lower than this value, IV, the comparator generates at this point here a pulse, as shown here, and then the programmable one-shot circuit is going to activate again the gate by generating a pulse with the same time interval TON. So basically this is the operation of a DC-DC converter under TON control. So as we are summarizing here, we have two control parameters. One is the on time, TON, that we are going to use to activate the switch. And the other control parameter is the value of the valley current of the inductor IV. Also, we have to note that this is a variable switching frequency control method because we are not fixing the switching period T. We are reaching the end of the period when the current reaches the minimum value IV at this point here. So this is an interesting control method that is very used in many applications of DC-DC converters and also in LED drivers. So we are going to see how to implement this control circuit in LTspice. We are going to create a new component for our library so we can use this device in future applications. We have everything that we need in our Simulink compatible control library. The main block is the one-shot circuit. So we have developed this block in this video, how to create a Simulink compatible control library number 3. And in this block we can inject the value of the on time through this input here and with this gain. So for example, this means that if we are selecting here T gain equal to 1 micro, means that if we put here at this point 1 volt, the output is going to generate a pulse of 1 microsecond. For example, in this case we are injecting here 4 volts, so the output is going to be 4 microseconds. And then we use here the comparator at which we are injecting the value of the valley current and here the value of the current through the inductor, which is sensed using this sensor, which is also available from the Simulink compatible control library, so that finally with the comparator we can generate the clock signal for the one-shot circuit. Here we have an example of a buck converter. These are the other elements, the gate and driver, also available from our library, and the rest of the elements. So now we are going to do a simulation to check that this circuit is going to operate correctly. So here we have the circuit in LTspice. We are going to do a transient simulation. Here we have the buck converter, and here we have the control circuit as we have just seen. So now we can run the simulation and see the results. For example, we can take a look at the output voltage. We are reaching a value of nearly 5 volts at the output with these values of the T-on time, which is 4 microseconds, and the value of the current is 400 milliamperes. So let's see other waveforms. Here we can take a look at the current that we are sensing here. This is the current through the inductor. So this value here is around 400 milliamperes, as we can see. Then maybe we can see other signals to understand better the behavior of the circuit. The clock signal here, and maybe here we can represent the value signal, so is this value here, and the clock signal. So maybe we can see this better if we select here 2 volts to see the pulses, and maybe we can add another pane and see the driving signal here. Again, if we select here 2 volts, we can see better the pulses. So as we can see, it is operating as expected. Let's do a zoom here so we can see the pulses coming out of the comparator. This is the on time, which we can check that is going to correspond approximately to the value of 4 microseconds. So everything is operating well. Maybe we can do some change. For example, if we increase the on time here to 5 microseconds and run the simulation again, then we can see that the output voltage is a little bit higher. We can also play with the IV value. For example, we can decrease this value to 200 milliamperes, run the simulation again. So now we can see that the ripple has increased. And also even we can use here a very small value, for example 1 milliampere, so that now we are operating in critical conduction mode. The value here of the current through the inductor is almost 0, and then we get a maximum value after the T-on time. Of course, now the output voltage is much lower, only 2 volts. So in principle, everything is working well. So now we can go ahead and create our new component for LTspice. So here we can see the implementation. This is the symbol that we are going to use. The name is my T-on controller, T-on-C. We have 3 inputs, as we can see here: the T-on time input, the value of the current, and the sensed current, the comparator, the one-shot circuit, and then we have these 3 outputs. The most important one is this one here, the driving signal for the gate, but I think that it's also interesting to generate other signals, which is very easy. We can generate the inverse signal here of the driving signal, just in case it can be interesting. And then also we are generating here the clock signal, which is generated from the comparator. Finally, this is the description. As you can see, it's very simple because we have only these 2 elements in our controller. And if you are not familiar with how to create new components in LTspice, please take a look at these 2 videos, LTspice number 3 and LTspice number 4. Finally, a comment here about the one-shot circuit. There is a back correction made in this component because I tested this component in different applications and I detected a small problem that we can find when using this component, and the problem is in this capacitor here, C2, which is the capacitor that captures the value of the time at a given instant when we are going to generate the pulse from the one-shot circuit. So in the original circuit we selected 1 nano for this capacitor, but I detected that this value is too small, so it is better to change this capacitor to 1 micro. In this way, when we close this switch to get the value of the time, we are going to have a new value of the charging time constant of this capacitor here, which is equal to 1 milliohm, which is the resistance of this switch here, times 1 microfarad. So the charging time constant is 1 nanoseconds, which is very small, and it's small enough. Before it was 1 picoseconds. And now when the switch is again open and this capacitor has to remain charged, of course it is going to be discharged a little bit through the input resistance of this other here, and the discharging time constant now is the input resistance of the other, which is 10 megaohm times the value of the capacitor, 1 microfarad. So now it's about 10 seconds. Before it was 10 milliseconds, and I detected that this value could be too small, and then this capacitor was going to be discharged a little bit and create some error in the generation of the on time at the output of the one-shot circuit. So this is the correction, just to change this capacitor C2 to the value of 1 microfarad. So this can be done here by changing this value in the description in LTspice, or changing this value of 1 nanofarad to 1 microfarad, but this has already been done in the last version of control.lib. So if you want to have the last version, you can go to my website, and then there you can download this last version with this correction. So I recommend you to always download the last version of the library control.lib, because I will try to keep this library updated and to solve any bug, any issue that can appear in the library. So before using any new component, please download the last version of this library. So as usual, if you want to save time, you can go to my website. Here is the link, and then in the part corresponding to resources, you can find here the component my TON controller already implemented, and you can download the symbol and the description of the component. And as I told you before, here you can download the last version of the control library, which has been updated very recently. Finally, to close this presentation, we are showing here the same converter as before, but now using our new component. I can click on this, right click, and then see the different parameters. Here we have the gain for the on time, the time gain, and then here we have selected 4 volts, so it corresponds to 4 times 1 micro, 4 microseconds, and this is the valley current is 400 milliamperes. We are sensing the current here through this sensor, and then we can run the simulation and see the same results as before. We can add another pane and then show the current and everything. So here we have, for example, the valley current, and we can see that it is operating correctly. So please take a look if you are interested, try this component and let me know if this component is useful for you or if you have any comment or question. With this, we conclude this video today. I hope that this information is interesting for you. Thank you very much for watching the video and I hope to see you in the next one. Goodbye now.